Tonight, the most dangerous part of Artemis II is not the launch, it is the journey home. After flying farther from Earth than any human mission in more than 50 years, the crew must survive deep space radiation, a high-speed return through Earth's atmosphere, and a razor-thin re-entry corridor where even a small mistake could mean disaster. This is the story of how NASA plans to bring Artemis II back alive. If space documentaries like this matter, please like the video, subscribe to the channel, and join us for the journey. The Earth and the Moon exist together as a bound system, held in a steady exchange of motion governed by gravity. Earth, with its greater mass, anchors the system, while the Moon follows an orbit that averages about 384,000 kilometers away. This distance is not constant. Observations indicate that the Moon moves in an elliptical path, sometimes closer, sometimes farther, but always remaining within a predictable range defined by gravitational balance. The space between them is not empty in a practical sense. It forms a region shaped by forces that extend far beyond visible matter. Within this system, Artemis II prepares to travel not simply from one body to another, but across layers of influence that extend outward from Earth and inward toward the Moon. The mission exists inside a structure defined by motion, where every object follows a path determined by velocity and gravitational pull. Earth rotates beneath a thin atmosphere, completing one turn every 24 hours, while the Moon orbits Earth in about 27 days. Together, they move around the Sun, creating a larger orbital pattern that frames the mission within the broader solar system. The gravitational relationship between Earth and the Moon creates what is known as a two-body system, though in reality it is influenced by the Sun and other planetary bodies. The centre of mass of this system, called the barycenter, lies within Earth, but not at its exact centre. This slight offset causes Earth itself to move subtly as the Moon orbits. For a spacecraft leaving Earth, this motion matters. The departure trajectory must account for the shifting positions of both bodies, ensuring that the path aligns not only with where the Moon is, but where it will be. The Earth-Moon system also defines a boundary of influence known as the Hill sphere, a region where Earth's gravity dominates over that of the Sun. Artemis II operates well within this boundary, but its journey stretches toward the outer edge of Earth's immediate control. Within this sphere, motion remains primarily governed by Earth, though the influence weakens with distance. As the spacecraft moves outward, it enters a gradual transition zone where Earth's hold diminishes and the Moon's begins to assert itself. Light from the Sun fills this space continuously, reflecting off both Earth and the Moon. Earth appears as a bright sphere, covered by clouds and oceans, while the Moon reflects a softer, grey light. The contrast between them is visible even across vast distances. The brightness of Earth can illuminate the Moon's surface, a phenomenon known as Earthshine. While the Moon's phases change as it moves through its orbit, these visual changes are the result of geometry, not intrinsic variation. The same rules guide the path of a spacecraft, where position and angle determine what is seen and how motion unfolds. Temperature in this system varies widely depending on exposure to sunlight. Without an atmosphere to distribute heat, the space between Earth and the Moon experiences sharp differences between illuminated and shadowed regions. A spacecraft moving through this environment must manage these changes carefully. Materials expand and contract with temperature, and internal systems must remain stable despite external fluctuations. The design of Artemis II reflects an understanding of these conditions, ensuring that the vehicle can endure prolonged exposure without atmospheric protection. Radiation also permeates this region. Beyond Earth's atmosphere, High-energy particles from the Sun and distant cosmic sources move freely. Earth's magnetic field provides some protection, but its influence does not extend indefinitely. Within the Earth-Moon system, radiation levels vary depending on position relative to this magnetic shield. The spacecraft's path must take into account not only distance, but exposure over time. Shielding and mission timing become essential elements in reducing risk. Communication across this system depends on the constant transmission of radio waves. These signals travel at the speed of light, taking a little more than 1 second to reach the Moon from Earth. This delay is small but measurable. It introduces a separation between action and response, requiring careful coordination between the spacecraft and mission control. As Artemis II moves through the Earth-Moon system, its position changes continuously, and communication must adapt to these shifting distances. Gravity remains the dominant force shaping every aspect of the mission. It governs the launch, the trajectory, the return, and the final descent. Within the Earth-Moon system, gravity does not act as a single uniform pull, but as a field that changes with position. The spacecraft moves along a path determined by this field, following curves rather than straight lines. These paths, known as orbits and trajectories, are calculated with precision based on well-understood physical laws. The system itself is stable over long periods. The Moon is gradually moving away from Earth at a rate of a few centimeters per year, a result of tidal interactions. This slow change does not affect the immediate mission, but it reflects the dynamic nature of the system. Nothing remains completely fixed. Every motion contributes to a larger pattern that evolves over time. Artemis II exists within this framework as a temporary presence, a human-made object moving through a natural system that has persisted for billions of years. The mission relies on understanding this system in detail, from the largest scales of orbital motion to the smallest variations in gravitational influence. Each calculation builds on observations refined over decades, forming a foundation that allows the spacecraft to travel safely across a vast and complex environment. The Earth-Moon system, though familiar in appearance, reveals its complexity through these interactions. It is not merely a distance to cross, but a structure to navigate. The spacecraft does not move independently of this system. It becomes part of it, following the same rules that govern planets and moons. Its journey reflects a balance between human intention and natural law, where precision and understanding replace force. Within this outermost view, the mission appears as a small motion across a wide expanse, a controlled passage through a region defined by gravity, light, and time. The path is shaped long before the spacecraft leaves Earth, embedded in calculations that align motion with opportunity. Every aspect of the journey begins here, within the broad structure of the Earth-Moon system, where distance, force, and motion combine to form the stage on which the mission unfolds. Beyond the immediate gravitational structure of the Earth-Moon system lies the region known as cislunar space, the broad expanse that stretches between Earth's upper influence and the Moon's domain. This region is not empty in a simple sense. It contains a thin distribution of particles, fields, and radiation that together form an environment both subtle and persistent. Artemis II moves through this region for much of its journey, and its conditions shape the mission in ways that are not visible but remain constant. The density of matter in cislunar space is extremely low. Individual atoms and charged particles drift across vast distances, rarely interacting. Most of these particles originate from the solar wind, a continuous flow of charged particles emitted by the Sun. This wind carries electrons and protons outward at speeds of hundreds of kilometers per second, spreading through the solar system and filling the space between planets. As these particles pass through the Earth-Moon region, they create a background environment that is always present, even when it is not directly observed. Within this flow, variations occur. The Sun does not emit a perfectly steady stream. Observations indicate that solar activity can increase the intensity of the solar wind, especially during events such as solar flares or coronal mass ejections. These events release bursts of energetic particles that travel outward and can reach cislunar space within hours or days. It remains uncertain exactly how each event will interact with a spacecraft, but the potential for increased radiation exposure is well understood. Mission planning takes into account these variations, using monitoring systems to track solar conditions in real time. Radiation in cislunar space comes from multiple sources. In addition to the solar wind, there are high-energy particles known as galactic cosmic rays. These originate outside the solar system, likely from distant supernova remnants and other energetic astrophysical processes. They travel at nearly the speed of light and penetrate deeply into materials, unlike solar particles, which can vary with solar activity. Cosmic rays provide a steady background of radiation. Their intensity changes slightly with the solar cycle, but they remain present at all times. The interaction of these particles with a spacecraft produces secondary effects. When high-energy particles strike the outer structure, they can generate cascades of lower-energy particles inside. This process increases the complexity of the radiation environment within the spacecraft. Shielding reduces exposure, but it does not eliminate it completely. Materials are chosen carefully to balance protection with weight, as heavier shielding can increase the overall mass of the vehicle and affect its trajectory. Micrometeoroids also pass through cislunar space. These are small particles, often no larger than grains of sand, that travel at high velocities relative to a spacecraft. Their origins vary. Some come from comet debris, while others result from collisions between asteroids. Despite their small size, their speed gives them significant energy. A micrometeoroid impact can damage surfaces, especially if it strikes critical components. The probability of a major impact during a single mission remains low, but it is not zero. Spacecraft are designed with protective layers to absorb or deflect these impacts. The electromagnetic environment in cislunar space is shaped by the absence of a strong planetary magnetic field. Far from Earth, the protective influence of its magnetosphere weakens, and the solar wind flows more freely. This creates a region where electric and magnetic fields fluctuate, influenced by solar activity and the motion of charged particles. These fields can interact with spacecraft systems, especially those involving electronics and communication. Careful design ensures that systems remain stable despite these external influences. Temperature in this region depends primarily on exposure to sunlight. Without an atmosphere to moderate heat, surfaces facing the sun can reach high temperatures, while shaded areas can become extremely cold. The difference between these extremes can exceed hundreds of degrees Celsius. Artemis II manages this variation through thermal control systems that distribute heat and protect sensitive components. The spacecraft rotates slowly at times to balance exposure, preventing one side from overheating while the other cools excessively. Light in cislunar space comes almost entirely from the sun. There is no scattering by air, so shadows are sharp and contrasts are strong. Objects in direct sunlight appear bright, while those in shadow become nearly invisible. This stark lighting environment affects navigation and observation. Instruments must adjust to rapid changes in brightness, and surfaces must be designed to reflect or absorb light in controlled ways. Navigation through cislunar space relies on precise tracking and calculation. The spacecraft's position is determined using a combination of onboard sensors and signals from Earth. Small adjustments are made using thrusters, correcting the path as needed. Even minor deviations can grow over time, so continuous monitoring is essential. The path is not a straight line, but a carefully shaped curve, influenced by gravity and initial velocity. Communication across this region remains steady but requires careful alignment. Radio signals must be directed toward Earth, and the spacecraft's orientation affects the strength of the connection. As distance increases, signal strength decreases, requiring more sensitive receivers. The delay in communication also grows slightly, though it remains within a few seconds. This delay requires that some operations be handled autonomously by the spacecraft. Time in cislunar space is measured not only by clocks but by motion. The spacecraft follows a trajectory defined by initial conditions set at departure. Once established, this path unfolds according to physical laws, with only minor corrections needed. The predictability of this motion allows mission planners to anticipate future positions and conditions with high accuracy. Cislunar space, though quiet and sparse, presents a continuous set of conditions that must be managed carefully. It is not a region of sudden changes but of steady influences that accumulate over time. Radiation, temperature, particle impacts, and electromagnetic fields all contribute to an environment that demands resilience and precision. Artemis II moves through this region as a controlled system, designed to endure and adapt. Within this broad expanse, the spacecraft remains isolated from Earth in a physical sense, yet connected through signals and shared motion. The journey across cislunar space forms the longest portion of the mission, where distance increases and the familiar presence of Earth begins to diminish. The environment remains consistent, governed by the same solar and cosmic forces that shape all of interplanetary space, and the spacecraft continues its path within this steady, unseen flow. At greater distance from Earth, the spacecraft enters a region where the planet's magnetic field extends outward in a stretched and complex form. This region, known as the outer magnetosphere, marks the boundary where Earth's magnetic influence begins to weaken under the constant pressure of the solar wind. The magnetosphere itself forms as Earth's internal magnetic field interacts with charged particles flowing from the Sun, creating a protective bubble that surrounds the planet. In the outer regions of this structure, the balance between Earth's field and solar forces becomes less stable and more variable. The magnetosphere does not form a perfect sphere. On the side facing the Sun, it is compressed, pushed inward by the solar wind. On the opposite side, it stretches far into space, forming a long tail known as the magnetotail. This tail can extend for hundreds of thousands of kilometers, well beyond the Moon's orbit at times. Artemis II moves through portions of this extended structure, where the magnetic field is weaker and more dynamic than closer to Earth. Within the outer magnetosphere, charge particles are guided by magnetic field lines that curve and shift in response to solar activity. These particles include electrons and ions that originate both from the solar wind and from Earth's upper atmosphere. Their motion follows the invisible paths defined by the magnetic field, spiraling along lines and drifting across regions of varying intensity. The density of these particles is lower than in the inner magnetosphere, but their behavior is more influenced by external conditions. The boundary between the magnetosphere and the solar wind is called the magnetopause. This surface is not fixed. Observations indicate that it moves inward and outward depending on the strength of the solar wind. During periods of increased solar activity, the magnetopause can be pushed closer to Earth, compressing the magnetosphere. During quieter periods, it expands outward. Artemis II's trajectory may pass near or through this shifting boundary, where conditions can change over short timescales. Beyond the magnetopause lies the solar wind in its more direct form, but within the outer magnetosphere there is a mixture of both influences. Magnetic reconnection, a process where magnetic field lines break and reconnect, can occur in this region. This process releases energy and accelerates particles, creating bursts of motion and localized changes in the environment. It remains uncertain exactly how frequently such events affect a specific trajectory, but their presence is well established through observation. The magnetotail, extending away from the Sun, contains two lobes separated by a thin region known as the plasma sheet. In this sheet, particle density is higher and energy exchange occurs more actively. Artemis II may pass through or near this region, where the interaction between solar and terrestrial influences becomes more pronounced. The plasma sheet is not uniform. It shifts and fluctuates, responding to changes in solar wind pressure and magnetic alignment. Radiation levels in the outer magnetosphere differ from those closer to Earth. While the intense radiation belts are located inward, the outer region still contains energetic particles that can affect spacecraft systems. These particles are less confined and more influenced by solar conditions. Their distribution can change rapidly, especially during geomagnetic storms triggered by solar events. Monitoring systems track these changes, allowing mission controllers to assess potential risks. Electric currents flow within the magnetosphere, driven by the motion of charged particles. These currents create additional magnetic fields that interact with the main field of Earth. In the outer regions, these currents can become more irregular, influenced by variations in the solar wind. The resulting electromagnetic environment is complex, with fields that vary in strength and direction over time. Spacecraft systems must be designed to operate reliably within this shifting context. Temperature in the outer magnetosphere is not defined in the same way as in an atmosphere. Instead, it refers to the energy of particles. High-energy particles correspond to higher effective temperatures, even though the density remains low. This means that while the environment contains energetic particles, it does not transfer heat in a conventional sense. The spacecraft experiences temperature primarily through radiation from the Sun and its own internal processes. Communication signals passing through this region encounter minimal interference compared to lower altitudes, where atmospheric effects are stronger. However, variations in plasma density can affect signal propagation slightly. These effects are generally small but must be accounted for in precise measurements. The spacecraft maintains a steady link with Earth, adjusting orientation to keep communication systems aligned. The outer magnetosphere represents a transition zone. It is neither fully protected by Earth's magnetic field nor entirely exposed to the solar wind. Instead, it forms a boundary region where influences overlap and interact. The spacecraft moves through this region as part of its outward journey, experiencing a gradual change in environmental conditions rather than a sudden shift. The structure of the magnetosphere reflects a balance between internal and external forces. Earth's magnetic field originates deep within its core, generated by the motion of molten iron. This field extends outward into space, but its shape is constantly modified by the solar wind. The result is a dynamic system that responds to conditions far beyond Earth itself. Artemis II passes through this region with careful timing and trajectory design. The path avoids prolonged exposure to areas of higher particle activity when possible, while still following the necessary route toward the Moon. The spacecraft's systems are built to withstand the range of conditions expected in this environment, from low-density plasma to periods of increased particle flux. Within the outer magnetosphere, the sense of separation from Earth becomes more pronounced. The planet's magnetic influence remains present but less dominant. The spacecraft moves closer to a regime where solar forces play a greater role, and where the protective effects of Earth diminish. This transition is gradual, marked by changes in particle behavior and magnetic structure, rather than visible boundaries. The region remains quiet in appearance, with no visual markers to indicate the shifting conditions. Yet beneath this stillness, complex interactions continue, driven by forces that operate across vast distances. The spacecraft continues its path through this environment, guided by precise calculations and sustained by systems designed to endure these subtle but persistent influences. Closer to Earth, the spacecraft encounters a region where the magnetic field becomes more structured and the behavior of charged particles is more constrained. This region contains the Van Allen radiation belts, zones of energetic particles trapped by Earth's magnetic field. These belts form two main layers, each defined by the motion of charged particles that spiral along magnetic field lines while drifting around the planet. Artemis II must pass through these regions during its departure and return, and their properties shape one of the most carefully managed phases of the mission. The inner radiation belt lies closer to Earth, extending from about 1,000 to several thousand kilometers above the surface. It is dominated by high-energy protons, many of which originate from cosmic ray interactions with Earth's atmosphere. These protons become trapped by the magnetic field and remain in stable orbits, forming a persistent zone of radiation. Their energies are high enough to penetrate materials and affect electronic systems if exposure is prolonged. The outer radiation belt extends farther outward, reaching tens of thousands of kilometers into space. This belt is primarily composed of high-energy electrons. Unlike the inner belt, the outer belt is more variable. Observations indicate that its intensity can change significantly in response to solar activity. During geomagnetic storms, the population of energetic electrons can increase, altering the radiation environment over relatively short periods. It remains uncertain exactly how each storm will influence the distribution at any given time, but the overall pattern of variability is well understood. Between these two belts lies a region of lower particle density, sometimes referred to as a slot region. This area is shaped by interactions between particles and electromagnetic waves that scatter them out of the belts. The presence of this gap reduces overall exposure during passage, but it does not eliminate the need for careful timing and trajectory design. The motion of particles within the belts follows three primary behaviors. First, particles spiral along magnetic field lines, moving between the northern and southern hemispheres. Second, they bounce between mirror points, where increasing magnetic field strength reflects them back along their path. Third, they drift slowly around Earth, forming ring-like distributions. These combined motions create a stable yet dynamic structure that persists over time. Radiation exposure within the belts depends on both intensity and duration. Artemis II is designed to pass through these regions relatively quickly, minimizing the time spent in higher radiation zones. The trajectory is chosen to avoid the most intense areas, particularly within the inner belt. Shielding within the spacecraft provides additional protection, reducing the dose experienced by onboard systems and crew. Materials are selected to absorb or deflect particles, though complete shielding is not practical due to weight constraints. The biological effects of radiation are a central concern. High-energy particles can damage cells and increase the risk of long-term health effects. The mission design includes limits on acceptable exposure based on established guidelines. Monitoring systems track radiation levels in real time, allowing adjustments if conditions differ from expectations. Observations indicate that short-duration passage through the belts, combined with shielding, keeps exposure within acceptable ranges. Electronic systems are also affected by radiation. Charge particles can cause single-event effects, where a particle striking a microelectronic component alters its state. This can lead to temporary errors or, in rare cases, permanent damage. To mitigate this risk, systems are designed with redundancy and error correction mechanisms. Critical components are shielded more heavily, and software can detect and correct anomalies. The magnetic field that traps these particles originates from Earth's core, but its structure in space is shaped by the interaction with the solar wind. This interaction compresses the field on the sunward side and stretches it on the opposite side, influencing the shape and location of the belts. As a result, the belts are not perfectly symmetrical. Their boundaries shift slightly with changes in solar conditions, though their overall structure remains consistent. Temperature within the belts is again defined by particle energy rather than thermal contact. The spacecraft's thermal environment continues to depend on sunlight and internal heat. However, radiation can contribute to heating of materials over time, particularly in sensitive components. Thermal control systems account for this additional input, maintaining stable operating conditions. Navigation through this region requires precise timing. The spacecraft's velocity and path determine how long it remains within each belt. Even small changes in trajectory can alter exposure. Mission planners use detailed models of the radiation environment to select optimal paths, balancing efficiency with safety. These models are based on decades of observations from satellites and previous missions. Communication remains stable during passage through the belts. Though high-energy particles can introduce minor interference, systems are designed to maintain signal integrity, ensuring continuous contact with Earth. The spacecraft's orientation is managed to support both communication and shielding, aligning protective structures toward the most intense particle flows when possible. The passage through the Van Allen belts represents a controlled interaction with one of the most energetic regions near Earth. It is not a region of visible activity, but of invisible motion, where particles move at high speeds within a magnetic framework. The spacecraft crosses this region as part of its ascent outward, transitioning from the more sheltered environment near Earth to the broader conditions of cislunar space. Within this inner magnetospheric region, Earth's influence remains strong, but it is expressed through fields and particles rather than atmosphere. The belts form a boundary of energy that must be crossed with care. Artemis II moves through them as a brief but significant phase of its journey. Guided by precise planning and supported by systems designed to withstand this concentrated exposure, the structure of the belts reflects a balance between trapping and loss, where particles are continually captured and scattered. This balance maintains the belts over long periods, even as individual particles enter and leave. The spacecraft's passage does not alter this structure. It remains a transient presence within a stable system, moving through a region defined by forces that operate far beyond human scale. As the spacecraft exits this region, the intensity of trapped radiation decreases and the influence of Earth's magnetic field begins to fade once more. The path continues outward, shaped by the same principles that govern motion throughout the Earth-Moon system, carrying the mission beyond the concentrated energy of the inner magnetosphere. At the edge of Earth's dominant magnetic and gravitational influence lies the region of high Earth orbit, where the spacecraft completes its final preparations before committing fully to the path toward the Moon. This region exists beyond the densest radiation belts, yet still within the extended reach of Earth's gravity. Here, motion becomes less constrained by orbital patterns around the planet and more defined by the transition toward a new trajectory. Artemis II enters this zone after ascending from lower orbits, carrying with it the momentum built during launch and the guidance of precise navigation systems. High Earth orbit is not a single fixed altitude, but a range of distances where spacecraft can remain bound to Earth while experiencing reduced atmospheric drag and minimal interference from the planet's environment. The absence of atmosphere is complete in this region, and the spacecraft moves in near-perfect vacuum. Without air resistance, motion continues unless altered by propulsion. This allows for stable positioning while final trajectory adjustments are made. Gravity remains the central force, but its strength decreases with distance. The pull of Earth weakens gradually, following a predictable relationship where the force diminishes as the square of the distance increases. At these distances, the spacecraft is still firmly within Earth's gravitational domain. Yet the influence of the Moon begins to become measurable. This overlapping of gravitational effects creates a region where trajectory planning must account for both bodies simultaneously. The spacecraft's velocity in this region is carefully controlled. It must reach a speed sufficient to leave Earth's orbit without exceeding the limits that would complicate its path toward the Moon. This balance is achieved through a maneuver known as translunar injection. But before that maneuver occurs, the spacecraft stabilizes in high Earth orbit, aligning its orientation and systems. The timing of this phase is critical. The position of the Moon relative to Earth determines the precise moment when the spacecraft must accelerate. Light conditions remain stark and unfiltered. The Sun illuminates the spacecraft directly, while Earth appears below as a large, curved horizon, partially lit depending on its phase. The planet's surface features become less distinct with distance, blending into patterns of cloud and ocean. The Moon, still far away, appears as a small but defined object, its position slowly shifting against the background of stars as both bodies move along their orbits. Thermal conditions continue to fluctuate based on exposure to sunlight. The spacecraft rotates or adjusts its orientation to distribute heat evenly. Preventing localized extremes, radiators release excess heat into space, while insulation limits unwanted loss. These systems operate continuously, maintaining internal stability as the spacecraft prepares for the next phase of its journey. Radiation levels in high Earth orbit are lower than within the Van Allen belts but still present. The spacecraft has already passed through the most intense zones, and the remaining exposure comes from background sources such as cosmic rays and residual particles within the magnetosphere. Monitoring systems continue to track these levels, ensuring that conditions remain within expected limits. Communication with Earth remains strong and reliable. At this distance, signal delay is still minimal, and data transmission occurs with little interruption. Ground stations track the spacecraft's position with high precision, using radio signals to measure distance and velocity. These measurements allow for continuous refinement of the spacecraft's trajectory, ensuring alignment with the planned path. The orientation of the spacecraft becomes increasingly important. Before the main propulsion maneuver, it must be aligned precisely along the direction of intended acceleration. Even a small deviation in angle can result in significant changes in trajectory over long distances. Guidance systems use a combination of inertial measurements and star tracking to determine orientation. By comparing observed star positions with known patterns, The spacecraft can maintain accurate alignment without relying solely on external signals. Time in this region is marked by preparation rather than motion alone. Systems are checked, parameters are confirmed, and the spacecraft enters a state of readiness. The engines that will perform the translunar injection remain idle until the exact moment required. Fuel levels, pressure systems, and structural integrity are all monitored continuously. Each component must function within precise limits to ensure the success of the upcoming maneuver. The concept of orbit changes in this region. While the spacecraft is still technically in orbit around Earth, it is no longer following a simple circular or elliptical path. Instead, it occupies a transitional orbit that will soon be altered into a trajectory that extends outward toward the Moon. This transition is not abrupt. It is the result of a carefully timed acceleration that reshapes the spacecraft's path from a closed loop into an open curve. The surrounding space remains quiet in appearance, with no visible boundaries marking the shift from one region to another. Yet the underlying forces define a clear progression. Earth's influence, though still present, becomes less dominant, and the conditions that govern motion begin to reflect the broader environment of cislunar space. Artemis II exists in this region as a system in balance, holding its position and preparing for change. The spacecraft's structure, systems, and trajectory converge toward a single objective, the transition from Earth-bound motion to lunar-directed travel. This moment does not occur suddenly but emerges from a sequence of precise adjustments, each building on the last. The high Earth orbit departure zone represents the final stage within Earth's immediate control. Beyond this point, the spacecraft will move along a path that extends far beyond the planet's immediate environment. The forces that guide its motion will shift, and the conditions it encounters will reflect a different balance of influences. Within this region, the mission remains anchored to Earth, both physically and operationally. Communication is direct, control is continuous, and the environment, though distant, is still shaped primarily by the planet. The spacecraft's readiness here determines the success of all that follows, as the transition from orbit to trajectory depends on precision established in this quiet and controlled space. The moment of translunar injection defines a change in motion, where the spacecraft shifts from a path bound to Earth into a trajectory that extends outward toward the Moon. This transition occurs through a controlled acceleration that increases the spacecraft's velocity to a precise value, allowing it to overcome the constraints of its previous orbit. The maneuver is not an escape in the absolute sense, as Earth's gravity continues to act upon the spacecraft, but it reshapes the path into a long arc that reaches toward the Moon's orbit. The physics governing this motion is based on conservation of energy and momentum. In a stable orbit, the spacecraft balances its forward velocity with the inward pull of gravity, creating a closed path around Earth. During translunar injection, the engines provide additional energy, increasing velocity so that the path no longer curves back toward Earth in a closed loop. Instead, it stretches outward, forming an elongated trajectory that intersects the region where the Moon will be. This maneuver is performed at a specific point in the spacecraft's orbit, where the direction of motion aligns with the desired path. The timing must match the position of the Moon, which continues to move along its orbit during the spacecraft's journey. Calculations account for this motion, ensuring that the spacecraft does not aim for where the Moon is at the moment of departure, but where it will be when the spacecraft arrives. This requires precise knowledge of orbital mechanics and accurate tracking of both bodies. The engines fire for a defined duration, producing thrust that accelerates the spacecraft along its direction of travel. The amount of thrust and the length of the burn determine the final velocity. Too little acceleration would leave the spacecraft in a higher but still closed orbit around Earth. Too much would send it on a path that misses the Moon entirely. The margin for error is small, and the maneuver is executed with careful monitoring of performance. As the engines operate, the spacecraft experiences a steady force that alters its motion. Inside, systems adjust to the change, maintaining stability and orientation. The structure of the spacecraft distributes the forces evenly, preventing stress from concentrating in any single area. Once the burn is complete, the engines shut down, and the spacecraft continues along its new path without further propulsion, following the trajectory defined by the maneuver. The resulting path is often described as a free return trajectory in certain mission designs. In this configuration, the spacecraft follows a curve that naturally loops around the Moon and returns toward Earth without requiring a major propulsion event at the Moon itself. This path relies on the gravitational interaction between Earth and the Moon, using their combined influence to guide the spacecraft. Observations and calculations indicate that such trajectories can provide an added margin of safety, though specific mission parameters determine whether this approach is used. During this phase, the spacecraft begins to move away from Earth at increasing distance. The planet gradually becomes smaller in view, though it remains the dominant gravitational influence. The Moon, still distant, grows slowly larger as the spacecraft approaches. The trajectory is not a straight line, but a curved path shaped by the continuous pull of Earth's gravity. Even as the spacecraft moves outward, Earth's influence bends its motion inward, creating a balance that defines the arc. Velocity changes throughout this journey. Immediately after the burn, the spacecraft reaches its highest speed relative to Earth. As it moves outward, gravity slows it gradually, converting kinetic energy into gravitational potential energy. This slowing is expected and accounted for in the trajectory design. By the time the spacecraft nears the Moon, its velocity relative to Earth will have decreased significantly. While the Moon's gravitational influence begins to alter its motion further, the environment during this phase remains similar to that of cislunar space. The spacecraft is beyond the densest regions of Earth's magnetosphere, though traces of magnetic influence may still be present depending on position. Radiation from solar and cosmic sources continues to affect the spacecraft, and thermal conditions remain governed by exposure to sunlight and shadow. Navigation becomes increasingly dependent on precise measurements of position and velocity. Small deviations introduced during the burn can grow over time, so tracking systems continuously assess the spacecraft's path. Corrections, if needed, are made using small thrusters that adjust velocity by slight amounts. These adjustments ensure that the spacecraft remains on course toward its intended path around the Moon. Communication with Earth continues, though the increasing distance introduces a slightly longer delay. Signals still travel quickly, but the separation becomes more noticeable. Commands and data flow between the spacecraft and ground control, maintaining coordination throughout the journey. The spacecraft also operates with a degree of autonomy, capable of maintaining its orientation and systems without constant input. The concept of trajectory during translunar injection reflects a transition from controlled propulsion to passive motion governed by gravity. Once the engines shut down, the spacecraft follows a path determined by initial conditions and external forces. This path can be predicted with high accuracy, allowing mission planners to anticipate future positions and plan subsequent maneuvers. The success of this phase depends on the precise execution of the injection maneuver. It represents a point where preparation and calculation converge into a single event that defines the rest of the outbound journey. The spacecraft moves from a region of stable orbit into a dynamic path that connects Earth and Moon. guided by the interplay of motion and gravity. Within this region, the spacecraft is no longer held in place by continuous propulsion or atmospheric interaction. It moves freely, following a path that extends across tens of thousands of kilometers. The forces acting upon it are constant yet subtle, shaping its motion without direct contact. The trajectory unfolds gradually, carrying the spacecraft outward along a curve that reflects the underlying structure of the Earth-Moon system. As the distance from Earth increases, the transition becomes more evident. The spacecraft leaves behind the conditions of high Earth orbit and enters a path defined by its initial acceleration and the gravitational field it moves through. The translunar injection marks the beginning of this extended motion, setting the spacecraft on a course that will carry it through the vast region between Earth and the Moon. Beyond the immediate influence of the translunar injection maneuver, the spacecraft continues along a long, curved path through what can be described as the Deep Space Transit Corridor. This region lies between the dominant gravitational zones of Earth and the Moon, where neither body fully controls the spacecraft's motion. Instead, the spacecraft follows a trajectory shaped by the combined and gradually shifting pull of both, moving through a space that appears still yet is defined by continuous, subtle forces. Distance from Earth increases steadily in this region. The planet, once large and detailed, becomes smaller, its surface features blending into broad patterns of light and shadow. The blue of the oceans and the white of the clouds remain visible, but fine detail fades with increasing separation. The curvature of Earth remains distinct, though it occupies a smaller portion of the sky. This visual change reflects the physical reality of motion. Where the spacecraft moves outward along a path that gradually reduces Earth's apparent size without altering its gravitational presence entirely. The Moon, in contrast, grows slowly larger. At first it appears as a distant object. Its surface features faint and indistinct. As the spacecraft progresses along its path, the Moon's disk becomes more defined, revealing variations in brightness that correspond to its surface composition. These changes occur gradually, without sudden transitions, reflecting the steady nature of motion through this region. Gravity continues to act upon the spacecraft from both Earth and the Moon. The balance between these influences shifts as distance changes. Initially, Earth's pull remains stronger, guiding the trajectory inward toward the curved path established during injection. As the spacecraft moves farther away, Earth's influence weakens, while the Moon's grows stronger. This transition is continuous, with no sharp boundary marking the point where one force overtakes the other. Velocity during this phase decreases relative to Earth as the spacecraft climbs outward against the planet's gravitational pull. This reduction in speed is a natural consequence of energy conservation. The initial acceleration provided during translunar injection gradually converts into potential energy as the spacecraft moves farther from Earth. At the same time, relative to the Moon, the spacecraft begins to gain influence, preparing for the next stage of motion as it approaches the region where lunar gravity becomes more significant. The environment of the Deep Space Transit Corridor remains sparse. The density of particles is extremely low, with only occasional interactions between the spacecraft and the surrounding medium. Solar radiation continues to provide the primary external influence, delivering a steady flow of energy that affects both thermal conditions and radiation exposure. The absence of a strong magnetic field means that the spacecraft is largely exposed to these influences without the protective buffering present closer to Earth. Thermal management remains a constant process. Surfaces exposed to the sun absorb energy, while those facing away radiate heat into space. The spacecraft's systems regulate this exchange carefully, using insulation and radiators to maintain stable internal conditions. The slow rotation or controlled orientation of the spacecraft ensures that no single area experiences prolonged extremes of temperature. Radiation exposure continues from both solar and cosmic sources. Without the shielding effect of Earth's magnetosphere, the spacecraft encounters a more direct flow of energetic particles. Monitoring systems track this exposure continuously, and the spacecraft's design limits the impact through material selection and structural configuration. While the environment is more exposed, it is also more uniform, lacking the concentrated zones of trapped radiation found closer to Earth. Navigation in this region depends on precise tracking and small adjustments. The spacecraft's position is determined using a combination of onboard instruments and signals from Earth. Star trackers provide orientation by comparing observed star patterns with known reference maps. Radio tracking measures distance and velocity relative to Earth, allowing mission controllers to refine the trajectory. Small thruster firings correct any deviations, ensuring that the spacecraft remains aligned with its intended path. Communication becomes slightly more delayed as distance increases. Signals take longer to travel between the spacecraft and Earth. Though the delay remains within manageable limits, this delay introduces a gradual shift in operations, where some functions rely more on onboard systems and less on immediate ground control input. The spacecraft maintains continuous communication, transmitting data about its condition and receiving updates as needed. The sense of isolation in this region is defined by distance rather than absence. Earth remains visible, though diminished, and communication persists without interruption. The spacecraft moves through a region that is physically vast but governed by predictable laws. Its path is not random, but follows a carefully calculated trajectory that unfolds over time with high precision. Light conditions remain consistent, dominated by direct sunlight and deep shadow. The absence of atmospheric scattering creates sharp contrasts. Where illuminated surfaces appear bright and shadowed areas remain dark. This clarity aids in navigation and observation, allowing instruments to detect subtle changes in position and orientation. Time during this phase is measured through motion and distance. The spacecraft advances along its path at a steady rate, with each moment bringing it closer to the region where the Moon's gravitational influence will dominate. The duration of this transit is determined by the initial conditions set during translunar injection and the geometry of the Earth-Moon system at the time of departure. The deep space transit corridor represents a region of continuity. There are no visible boundaries or sudden changes, only gradual transitions in force and position. The spacecraft moves through this region as part of a larger trajectory, maintaining stability and direction through careful design and constant monitoring. Within this corridor, the mission reaches a midpoint in its outward journey. The spacecraft is no longer strongly bound to Earth, yet it has not fully entered the domain of the Moon. It exists between two centers of gravity, guided by the balance of forces that define the Earth-Moon system. This balance shapes the path forward, carrying the spacecraft along a curve that reflects the underlying structure of space and motion. As the spacecraft continues along its path, it enters a region where the gravitational influence of the Moon becomes increasingly significant. This region, often described as the lunar sphere of influence, marks the gradual transition from Earth-dominated motion to a regime where the Moon's gravity plays the leading role. The boundary is not a fixed surface, but a zone defined by the relative strengths of gravitational forces. Within this region, the Moon's pull begins to shape the spacecraft's trajectory more strongly than that of Earth. The distance at which this transition occurs depends on the positions and masses of both bodies. Calculations indicate that the Moon's sphere of influence extends to a distance of tens of thousands of kilometers from its center. As the spacecraft approaches this region, the curvature of its path begins to change. The trajectory, once primarily influenced by Earth, starts to bend in response to the Moon's gravity, guiding the spacecraft toward a close approach. The motion of the spacecraft in this region reflects a shift in reference. Relative to Earth, the spacecraft continues to move outward, but relative to the Moon, it begins to fall inward. This dual perspective illustrates the nature of gravitational interaction, where motion depends on the frame of reference. The spacecraft is not simply moving away from one body or toward another, it is responding to both simultaneously, with the balance gradually shifting. Velocity relative to the Moon increases as the spacecraft enters this region. While its speed relative to Earth has been decreasing, the growing pull of the Moon accelerates it along a new direction. This change in velocity is not caused by propulsion, but by gravity itself. The spacecraft gains speed as it descends into the Moon's gravitational well, converting potential energy into kinetic energy once again. The Moon appears larger and more detailed as the spacecraft approaches. Surface features such as craters, plains, and highlands become visible, defined by variations in brightness and shadow. The lack of atmosphere on the Moon means that these features are seen with sharp clarity, unaffected by scattering or haze. The surface reflects sunlight directly, creating strong contrasts between illuminated and shadowed regions. The gravitational field of the Moon is not perfectly uniform. Variations in mass distribution beneath the surface create localized differences in gravitational strength. These variations, known as mass concentrations or mascons, can influence the motion of objects in low lunar orbit. For a flyby trajectory such as that of Artemis II, the effect of these variations is smaller but still considered in precise calculations. Observations from previous missions provide detailed maps of these gravitational anomalies, allowing accurate prediction of their influence. The environment in this region remains consistent with deep space conditions. There is no atmosphere, and the density of particles remains extremely low. Radiation continues to come from solar and cosmic sources, with no significant change in intensity due to the Moon's presence. The Moon does not possess a global magnetic field comparable to Earth's, so it does not provide a large-scale protective shield. However, localized magnetic fields exist in certain regions of the lunar surface, though their effect on the spacecraft at this distance is minimal. Thermal conditions remain governed by exposure to sunlight. As the spacecraft approaches the Moon, reflected light from the lunar surface contributes slightly to the overall radiation environment. This reflected light, known as albedo, is weaker than direct sunlight but still measurable. The spacecraft's thermal systems continue to regulate internal conditions, maintaining stability despite external changes. Navigation becomes increasingly focused on the Moon as a reference point. Tracking systems incorporate measurements relative to both Earth and the Moon, refining the spacecraft's position with respect to its intended flyby path. The timing and geometry of this approach are critical. The spacecraft must pass at a specific distance and angle to achieve the desired trajectory for the return journey. Communication with Earth remains active, though the relative positions of Earth, Moon, and spacecraft can affect signal paths. As the spacecraft moves closer to the Moon, there are periods when the Moon may partially or fully block direct line-of-sight communication with Earth. These intervals are predicted in advance, and the spacecraft is prepared to operate independently during such times. The concept of gravitational spheres of influence provides a useful approximation for understanding motion, though the actual transition is continuous. There is no abrupt moment when Earth's gravity ceases to act or the Moon's begins. Instead, the forces combine, with their relative strength shifting smoothly as distance changes. The spacecraft follows a path that reflects this continuous interaction, guided by the combined gravitational field. The approach to the Moon represents a convergence of motion and timing. The spacecraft arrives at a point in space where the Moon's position and velocity align with the planned trajectory. This alignment is the result of careful planning and precise execution of earlier phases. Small deviations in earlier stages would lead to larger differences at this point, so the accuracy of navigation throughout the journey becomes evident here. The visual presence of Earth changes during this phase. As the spacecraft moves closer to the Moon, Earth appears farther away, though still visible as a bright object in the sky. Its phase changes depending on the relative positions of the Sun, Earth, and spacecraft. The contrast between the bright Earth and the darker lunar surface highlights the difference in reflectivity and composition between the two bodies. The spacecraft's motion in this region is increasingly shaped by the need to achieve a specific path around the Moon. The trajectory must allow for a close approach that uses the Moon's gravity to redirect the spacecraft toward Earth. This gravitational assist does not require propulsion but depends on the geometry of the encounter. The spacecraft's path bends as it passes by the Moon, altering its direction and setting the course for return. Within the lunar sphere of influence, the mission enters a phase where the Moon becomes the primary reference for motion. The spacecraft responds to its gravity, its position, and its surface features. The transition from Earth's dominance to the Moon's influence is complete not at a single point but across this region, where the balance of forces shifts steadily. The spacecraft continues along its path, drawn inward by the Moon's gravity, preparing for the close approach that defines the next stage of its journey. The region remains quiet and without visible boundaries, yet the underlying forces guide every aspect of motion. Artemis II moves through this zone as a precise system, responding to the changing balance of gravity that defines the space between Earth and Moon. As the spacecraft moves deeper into the Moon's gravitational influence, its trajectory brings it toward the far-side flyby region, a portion of space defined not only by proximity to the lunar surface, but also by its position beyond direct line of sight from Earth. This region lies behind the Moon relative to Earth, where the bulk of the lunar body interrupts the straight path of communication signals. The transition into this zone is gradual, marked by the increasing presence of the Moon in the spacecraft's field of view and the corresponding reduction of Earth's visibility. The Moon now occupies a large portion of the sky, its surface features sharply defined in the absence of atmosphere. Craters of varying sizes cover the terrain, formed over billions of years by impacts from asteroids and other celestial debris. Large, dark plains known as Maria contrast with brighter highland regions. These differences in brightness reflect variations in composition and age, with the Maria representing ancient volcanic flows and the highlands preserving older crust. The spacecraft's path takes it above this landscape, maintaining a distance that ensures both safety and the correct trajectory for its return. Gravity in this region is dominated by the Moon. The spacecraft accelerates as it approaches its closest point, gaining speed due to the increasing gravitational pull. This motion follows a predictable curve, with the path bending around the Moon in a smooth arc. The precise shape of this arc depends on the spacecraft's velocity and the angle of approach. Calculations ensure that the path will redirect the spacecraft toward Earth after the flyby, using the Moon's gravity as a natural guide. The far side of the Moon differs from the near side in both appearance and structure. It contains fewer large maria and more densely cratered highlands. Observations indicate that this difference arises from variations in crust thickness and geological history. The far side's thicker crust limited the extent of volcanic activity, preserving a more heavily cratered surface. As the spacecraft passes over this region, the texture of the surface appears more uniform in its ruggedness. With fewer smooth planes interrupting the pattern, communication with Earth becomes limited as the spacecraft moves behind the Moon. Radio signals travel in straight lines, and the Moon's solid body blocks this path. During this period, known as a communication blackout, the spacecraft operates independently. Systems continue to function according to pre-programmed instructions, maintaining orientation, monitoring conditions, and recording data. The duration of this blackout is determined by the geometry of the flyby and is known in advance. The absence of direct communication introduces a period of isolation, though it is expected and carefully planned. The spacecraft does not rely on real-time commands during this phase. Instead, it follows a sequence of actions defined before the blackout begins. This autonomy reflects the reliability of onboard systems and the predictability of the trajectory. Once the spacecraft emerges from behind the Moon, communication resumes and stored data is transmitted back to Earth. The gravitational interaction during the flyby alters the spacecraft's velocity vector. While the speed relative to the Moon increases during approach and decreases after passing the closest point, the overall effect is a change in direction relative to Earth. This process, often described as a gravity assist, allows the spacecraft to redirect its path without expending additional fuel. The Moon effectively transfers a small amount of its orbital momentum to the spacecraft, though the change to the Moon itself is negligible. The closest approach distance is chosen to balance multiple factors. A closer pass increases the strength of the gravitational interaction, allowing for a more pronounced change in trajectory. However, it also requires greater precision to avoid entering an unintended orbit or encountering surface hazards. The selected distance ensures that the spacecraft remains safely above the surface while achieving the desired path for return. The environment near the Moon remains similar to that of deep space, with extremely low particle density and no atmosphere. The lack of atmosphere means that there is no aerodynamic drag or heating during this phase. The spacecraft moves through a vacuum, influenced only by gravity and radiation. Surface reflections contribute slightly to the local light environment, but they do not significantly alter thermal conditions. Local variations in the Moon's gravitational field, caused by mass concentrations beneath the surface, can affect the trajectory slightly. These effects are well characterized through previous missions, allowing accurate prediction and compensation. The spacecraft's navigation systems account for these variations, ensuring that the path remains within expected parameters. Light and shadow on the lunar surface create a high contrast drisha. The sun illuminates portions of the terrain while leaving others in deep shadow. These shadows can persist for long periods in regions near the poles, though the flyby path typically crosses areas where illumination changes more gradually. The absence of atmospheric scattering results in sharp boundaries between light and dark, enhancing the visibility of surface features. As the spacecraft passes the point of closest approach, its motion begins to carry it away from the Moon. The gravitational pull decreases with distance, and the trajectory curves outward. The direction of motion now aligns with a path that leads back toward Earth. The transformation from approach to departure occurs smoothly, without any abrupt change, as the influence of the Moon gradually weakens. Earth begins to reappear from behind the Moon as the spacecraft moves out of the far side region. The planet's presence becomes visible once more, growing slightly in apparent size as the spacecraft continues along its return path. Communication signals are restored, and the connection between spacecraft and mission control resumes fully. The farside flyby region represents a moment of transition within the mission. It is defined by proximity to the Moon, the temporary loss of direct communication, and the gravitational interaction that redirects the spacecraft's path. The environment remains consistent with the vacuum of space, yet the presence of the lunar surface introduces a sense of closeness and structure not found in the more distant regions. Within this region, the spacecraft completes the outward portion of its journey and begins the return. The path ahead is shaped by the motion established during the flyby, carrying the spacecraft away from the Moon and back toward Earth. The forces at work remain the same, but their balance shifts once more, guiding the mission through the next phase of its trajectory. After passing the point of closest approach to the Moon, the spacecraft continues along a path that has been reshaped by the gravitational interaction. This moment marks the initiation of the return trajectory, where the direction of motion is no longer outward from Earth but begins to curve back toward it. The transition is not marked by a visible boundary or a sudden change in motion. Instead, it emerges from the geometry of the flyby, where the spacecraft's velocity vector has been redirected to intersect with Earth position at a later time. The return trajectory is defined by the combined influence of the Moon's gravity at the moment of closest approach and the continuing pull of Earth. As the spacecraft moves away from the Moon, its velocity relative to the Moon decreases, while its velocity relative to Earth begins to align with a path that leads inward. This change reflects the conservation of energy and momentum within the Earth-Moon system. No additional propulsion is required to initiate the return, as the necessary change in direction has already been achieved through the flyby. The shape of the return path resembles a long arc extending from the Moon back toward Earth. This arc is not symmetrical with the outbound path, as it depends on the precise conditions of the flyby, including the angle of approach and the distance of closest passage. Small differences in these parameters can alter the timing and geometry of the return, which is why the earlier phases of the mission are executed with high precision. As the spacecraft departs the Moon, the visual prominence of the lunar surface begins to diminish. The Moon, once occupying a large portion of the sky, gradually recedes, its features becoming less distinct. The contrast between bright highlands and darker Maria fades with distance, and the surface returns to a smaller, more uniform appearance. This visual change reflects the increasing separation, though the Moon's gravitational influence remains present for some time. Earth, in contrast, begins to grow slightly larger in view. Initially, it appears as a bright object emerging from behind the Moon, its phase determined by the relative positions of the Sun, Moon, and spacecraft. As the return trajectory unfolds, Earth becomes a more central reference point for navigation and orientation. Its gravitational pull strengthens as distance decreases, gradually becoming the dominant force once more. The environment during this phase remains consistent with deep space conditions. The spacecraft continues to move through a vacuum with extremely low particle density. Radiation from solar and cosmic sources persists, and thermal conditions remain governed by exposure to sunlight and shadow. The absence of a significant magnetic field in this region means that the spacecraft is largely exposed to these influences, though its design mitigates their effects. Navigation during the return trajectory focuses on maintaining alignment with the planned re-entry path. The spacecraft's position and velocity are continuously monitored, using both onboard instruments and signals from Earth. Any deviations from the intended trajectory are corrected with small thruster firings, ensuring that the path remains within the narrow limits required for a safe return. Communication with Earth resumes fully after the spacecraft emerges from behind the Moon. Signals travel across the increasing distance, carrying data about the spacecraft's condition and trajectory. The delay in communication remains small but noticeable, requiring coordination between onboard systems and ground control. The spacecraft operates with a degree of autonomy, maintaining stability and executing planned actions even when direct commands are not immediately available. The concept of free return trajectory becomes particularly relevant during this phase. In such a trajectory, the spacecraft's path naturally leads back to Earth, without requiring a major propulsion event after the flyby. This design provides a level of safety, as it ensures that the spacecraft will return even if certain systems fail. Observations and mission planning indicate that Artemis II incorporates elements of this approach, though specific details depend on the final mission profile. Velocity relative to Earth increases gradually as the spacecraft begins to fall back toward the planet. This increase is driven by Earth's gravitational pull, which accelerates the spacecraft as it moves inward. The process is the reverse of the outward journey, where velocity decreased as the spacecraft climbed away from Earth. The balance of energy remains consistent, with potential energy converting back into kinetic energy. The return trajectory must align with a specific entry corridor in Earth's atmosphere. This corridor is defined by a narrow range of angles and velocities that allow the spacecraft to re-enter safely. Too steep an approach would result in excessive heating and structural stress, while too shallow an approach could cause the spacecraft to skip off the atmosphere and return to space. The trajectory is therefore designed with precision, ensuring that the spacecraft arrives at the correct point with the correct conditions. The spacecraft's orientation during this phase is managed to support both communication and thermal control. Antennas remain directed toward Earth to maintain signal strength, while surfaces are positioned to balance exposure to sunlight. Internal systems continue to operate within stable parameters, supported by the spacecraft's design and ongoing monitoring. Time during the return trajectory is marked by a gradual reconnection with Earth. The increasing size of the planet in view, the strengthening of its gravitational pull, and the shortening communication delay all reflect the approach. The spacecraft moves along a path that has been defined since the moment of translunar injection, shaped by the interactions of gravity and motion across the Earth-Moon system. The return trajectory initiation represents a turning point within the mission, where outward exploration transitions into inward movement. The spacecraft carries with it the conditions established during the flyby, following a path that leads steadily back toward Earth. The forces at work remain consistent, but their balance shifts once more, guiding the spacecraft through the next stage of its journey. Within this region, the mission continues with a sense of continuity rather than change. The spacecraft remains in deep space, moving through an environment that appears unchanged, yet its direction and purpose have altered. The path now leads home, shaped by the same principles that governed its departure, unfolding gradually as distance decreases and Earth's presence becomes more prominent. As the spacecraft continues along its return path, it moves through a region where Earth's gravitational influence steadily increases, shaping the trajectory into a gradual inward fall. This phase, often described as the Earthbound deep space return, unfolds across a vast distance where the spacecraft transitions from the Moon's domain back into Earth's dominant sphere of influence. The change is continuous and measured, defined not by a sudden shift but by the steady strengthening of Earth's pull. Distance from the Moon increases, and its visual presence diminishes into a smaller, dimmer object against the background of space. The surface details that were once clearly visible fade into a uniform grey disk, eventually becoming a point of light. The Moon's gravitational influence weakens with distance, and its effect on the spacecraft's motion becomes secondary to that of Earth. This transition is gradual, with both forces acting simultaneously until Earth's dominance is fully re-established. Earth grows steadily larger in the spacecraft's view. At first it appears as a bright sphere with distinct coloration, the blue of oceans and the white of clouds becoming more defined as distance decreases. The curvature of the planet becomes more prominent, and the contrast between illuminated and shadowed regions reflects its rotation and the position of the Sun. This visual change corresponds directly to the spacecraft's inward motion, marking its progress through space. The trajectory during this phase is governed by gravitational acceleration toward Earth. As the spacecraft moves closer, its velocity relative to Earth increases. This acceleration results from the conversion of gravitational potential energy into kinetic energy, following well-established physical principles. The increase in speed is continuous, with the rate of change becoming more noticeable as the spacecraft approaches the planet. The environment remains consistent with deep space conditions. The density of particles is extremely low, and the spacecraft encounters minimal resistance. Radiation from solar and cosmic sources continues to affect the spacecraft, though the overall exposure remains within expected levels. The absence of a strong magnetic field in this region means that the spacecraft is still largely exposed to these influences, though Earth's magnetosphere lies ahead along the path. Thermal conditions remain governed by exposure to sunlight and shadow. The spacecraft continues to regulate its temperature through active systems that distribute heat and maintain stable internal conditions. The increasing brightness of Earth contributes a small additional source of reflected light, though its effect on thermal balance is limited compared to direct solar radiation. Navigation during this phase becomes increasingly focused on precise alignment with the re-entry corridor. The spacecraft's position and velocity are monitored continuously, using a combination of onboard sensors and signals from Earth-based tracking systems. Small adjustments are made using thrusters to correct any deviations, ensuring that the trajectory remains within the narrow limits required for safe atmospheric entry. Communication with Earth becomes more immediate as distance decreases. The time delay in signal transmission shortens, allowing for more direct coordination between the spacecraft and mission control. Data flows continuously, providing information about the spacecraft's condition, trajectory, and environment. Commands from Earth are received with minimal delay, supporting ongoing adjustments and system checks. The concept of trajectory during this phase reflects a controlled descent through space. Although the spacecraft remains far above Earth's atmosphere, its motion is directed inward, following a path that will intersect with the planet at a precise location and angle. This path is not adjusted through large propulsion events, but through careful planning and minor corrections that maintain alignment. The spacecraft's orientation is managed to support both communication and thermal control. Antennas remain directed toward Earth to maintain a strong signal, while surfaces are positioned to balance exposure to sunlight. Internal systems continue to operate within stable parameters, supported by the spacecraft's design and continuous monitoring. As the spacecraft approaches Earth, it begins to encounter the outer regions of the planet's magnetic field. The magnetosphere extends far into space, forming a boundary that the spacecraft will cross before entering the atmosphere. This boundary is not sharply defined, but its presence marks a change in the environment where charged particles become more influenced by Earth's magnetic field. The increasing influence of Earth's gravity also affects the shape of the trajectory. The path curves more sharply as the spacecraft draws closer, reflecting the stronger gravitational pull. This curvature is essential for guiding the spacecraft into the correct re-entry corridor. The timing and geometry of this approach are critical, as even small deviations can lead to significant differences in the entry conditions. The spacecraft's velocity continues to increase, reaching values significantly higher than those experienced during launch. This high speed is a necessary condition for returning from deep space, but it also introduces challenges for the upcoming atmospheric entry. The spacecraft must be designed to withstand the forces and heating that will occur as it encounters Earth's atmosphere at high velocity. The visual presence of Earth becomes dominant as the spacecraft nears the end of its deep space return. The planet fills a larger portion of the sky, with cloud patterns and surface features becoming more detailed. The boundary between day and night, known as the terminator, is visible as a curved line across the surface, indicating the division between illuminated and shadowed regions. The return through deep space represents a phase of convergence, where the spacecraft moves steadily toward its point of re-entry. The path has been defined by earlier maneuvers and gravitational interactions, unfolding with precision as distance decreases. The forces at work remain consistent, but their effects become more pronounced as the spacecraft approaches Earth. Within this region, the mission transitions from the vast expanse of deep space toward the structured environment of Earth's immediate surroundings. The spacecraft remains in a vacuum, yet the presence of the planet ahead signals the approach of a new set of conditions. The trajectory narrows toward a specific hadaf, where timing, angle, and velocity must align precisely. The Earthbound deep space return concludes as the spacecraft approaches the region where atmospheric interaction will begin. The environment remains quiet and stable, but the conditions ahead require exact preparation. The spacecraft continues along its path, guided by gravity and maintained by careful control, moving steadily toward the next phase of its journey. As the spacecraft leaves the broad quiet of deep space and approaches the Earth more closely, its path narrows toward a precise geometric condition known as the re-entry corridor. This corridor is not a physical channel in the atmosphere or a visible band surrounding the planet. It is a narrow range of approach angles and velocities that determine whether a spacecraft returning from the Moon can enter the atmosphere safely. Artemis II moves toward this condition gradually, guided by a trajectory that has been shaped since departure and refined through small corrections during the return. From a distance, Earth appears large and luminous, its cloud systems spreading across the curved surface in broad white forms above darker oceans and lighter land. The atmosphere itself is still too thin to be seen as a place of contact, yet its presence is visible as a delicate blue boundary along the edge of the planet. This thin layer, though slight in appearance, becomes the critical medium through which the spacecraft must pass. The challenge is not simply to reach Earth, but to meet the atmosphere at exactly the right angle. If the spacecraft approaches too steeply, it descends too quickly into denser air. In that case, the rate of compression and heating rises sharply, and the forces on the structure increase beyond the intended design limits. If the spacecraft approaches too shallowly, it does not descend deeply enough into the atmosphere to lose sufficient speed. In that case, it can skip outward again, returning to space on an unintended path. The safe corridor between these two outcomes is narrow. Observations from past lunar return studies and missions indicate that precise control of entry conditions is essential for survival. The spacecraft's velocity at this stage remains extremely high. Having fallen inward through Earth's gravitational field, it carries far more energy than a vehicle returning from low Earth orbit. This is one of the reasons a lunar return is more demanding than many earlier orbital missions. The heat shield, the structure beneath it, and the guidance system must all function together to manage an entry that begins with great speed and little margin for error. The danger of the mission is concentrated here, not because the process is chaotic, but because it must unfold within strict physical limits. The re-entry corridor is described in terms of flight path angle, a measure of how steeply the spacecraft approaches relative to the local horizontal at the top of the atmosphere. This angle is established before the spacecraft encounters significant air. By the time the atmosphere begins to matter, the essential geometry is already fixed. Small thruster firings made earlier in the return adjust this angle by minute amounts. A change that seems small in deep space can alter the eventual atmospheric entry by many kilometers. Navigation in this phase becomes an exercise in refinement. Ground tracking stations measure the spacecraft's position and velocity with increasing precision as Earth grows closer. Radio signals reflect the motion of the spacecraft through subtle shifts in frequency, allowing controllers to determine how fast it's moving toward the planet. Onboard systems compare inertial measurements with expected values, confirming that orientation and trajectory remain within limits. The result is a constant verification of alignment with the corridor. The spacecraft's shape matters greatly here. The Orion capsule is not symmetrical like a simple sphere. Its slightly offset form allows it to generate a modest amount of lift during atmospheric entry. Lift, in this context, means a force produced by the interaction between the capsule's shape and the surrounding air, directed partly upward relative to the flight path. This lift is small compared with the overall forces involved, but it gives the spacecraft some ability to control how deeply it descends and how quickly it sheds speed. That control becomes important only because the re-entry corridor is so narrow. Before the spacecraft reaches the upper atmosphere, its orientation must be set precisely. The heat shield must face forward, taking the full burden of the coming thermal load. The capsule rotates into entry attitude well before contact with significant air, using its reaction control thrusters to align itself. Once aligned, it maintains that posture with careful stability. The outer surface that will meet the atmosphere first is designed to absorb and shed intense heat through controlled erosion, a process known as ablation. The material gradually chars, melts, and carries heat away as it wears down. Communication with Earth remains available during this approach, though the time available for major decisions grows shorter as the spacecraft closes the remaining distance. By this stage, the mission is no longer about choosing among broad options. It is about confirming that the path already established remains correct. There is little room for large changes. The spacecraft is committed to entry, and the remaining work is to ensure that the conditions at atmospheric contact match the design. The Earth's atmosphere, seen from afar as a thin luminous edge, becomes conceptually thicker as the spacecraft approaches. Even though the first meaningful interaction will begin in the highest layers, the effects of the atmosphere depend on what lies below as well. The upper air begins the process, but the deeper layers determine how quickly the spacecraft slows and how strongly it is forced to decelerate. The corridor therefore represents not only an angle into the top of the atmosphere, but an entire path through its vertical structure. The ocean recovery zone far below remains outside the scope of this moment. What matters here is the invisible line in space where geometry becomes destiny. The spacecraft does not yet touch air, but every parameter now points toward that meeting. Mass, shape, speed, angle, and orientation all combine into a narrow solution that must hold. The crew inside experiences this phase as one of preparation and waiting. Systems are checked again. Displays confirm alignment. The vehicle remains enclosed in silence except for the steady functioning of onboard equipment. Outside, Earth fills more of the view. The dark background of deep space yields to the broad brightness of the planet, and the boundary between space and air approaches without visible motion in the atmosphere itself. There is no marked gate, no line that can be seen from afar. Yet the corridor is real in the language of physics, and the spacecraft is moving toward it with exacting care. This approach region is dangerous because it allows no improvisation. The laws governing motion through an atmosphere at lunar return speed are well understood, but they are not forgiving. Artemis II reaches this stage carrying the consequences of every earlier calculation and correction. The journey home narrows to a thin range of possible outcomes, and safety depends on arriving within that range. The spacecraft continues inward, aligned with the re-entry corridor, approaching the point where the first molecules of Earth's upper atmosphere will begin to change everything. The first contact with Earth's atmosphere begins high above the visible weather, in a region where the air is still extraordinarily thin. From the spacecraft's perspective, there is no sudden impact, no clear line where empty space ends and atmosphere begins. Instead, a small number of gas molecules start to strike the forward surface of the capsule. At first, these collisions are rare, but the spacecraft is moving so fast that even this faint contact begins to matter. Artemis II enters this upper atmosphere at a speed associated with return from the Moon, and that speed makes the earliest interaction with air one of the most demanding parts of the mission. The surrounding air in this region is made mostly of oxygen and nitrogen, though at these heights the molecules are spread far apart. Because the spacecraft travels at many kilometers per second, the air in front of it cannot move out of the way smoothly. It is compressed rapidly. This compression raises the temperature of the gas to extreme levels. The main cause of heating is not simple rubbing in the everyday sense, but the conversion of kinetic energy into thermal energy as the air is forced into a dense, hot layer ahead of the capsule. The faster the spacecraft moves, the more intense this process becomes. A shock wave forms in front of the capsule. A shock wave is a thin region across which pressure, temperature, and density change sharply. For a blunt-bodied spacecraft like Orion, this shock stands off from the surface rather than clinging tightly to it. That separation is important. It keeps the hottest gas slightly away from the heat shield and reduces the direct thermal load on the structure beneath. The capsule's shape is therefore a central part of its survival. The broad, rounded front is not an inefficiency. It is deliberate design for managing extreme entry conditions. As the gas behind the shockwave grows hotter, it changes in character. Molecules break apart into atoms, and some atoms lose electrons, creating ionized gas known as plasma. Plasma is a hot, electrically active state of matter. Around the capsule, it forms a glowing envelope produced by the intense energy of atmospheric entry. This glow is not decorative or incidental. It is the visible sign of air being driven to extreme conditions by the speed of the returning spacecraft. The heat shield begins to do its work immediately. Its outer material is designed to ablate, meaning it slowly erodes in a controlled way under intense heat, as the material chars, melts, and vaporizes. It carries energy away from the spacecraft. This sacrificial process protects the underlying structure and the crew inside. The shield does not remain unchanged through entry. It is expected to lose material. Its performance depends on that loss being controlled, predictable, and sufficient to keep internal temperatures within safe limits. The upper atmosphere is thin, but it is not negligible. Each descending kilometer increases the density of the air, and the forces on the spacecraft rise accordingly. The capsule begins to slow. This slowing is called deceleration, and it results from aerodynamic drag, the force exerted by air opposing motion through it. For a returning lunar spacecraft, deceleration does not happen all at once. It builds as the vehicle descends into denser layers. The crew experiences this as a growing load pressing them into their seats, while the structure of the spacecraft carries the force across its frame. Because Orion's shape can produce a modest amount of lift, the capsule is not simply falling straight downward through the air. Its orientation allows it to control the depth of its descent. By adjusting roll, the spacecraft can change the direction of that lift relative to its path, shaping how quickly it descends and how much heating and deceleration it experiences over time. This ability is especially important for a lunar return, where the entry energy is greater than for many low Earth orbit missions. The vehicle can spread the stress over a longer path through the atmosphere rather than accepting the full burden in a single steep plunge. In some planned return profiles, the spacecraft may perform what is known as a skip entry. In this approach, the capsule descends into the upper atmosphere, uses lift to rise back toward thinner air briefly, and then descends again. Observations and engineering studies indicate that this method can help manage heating and extend the range available for landing. It remains a controlled atmospheric interaction rather than a rebound into deep space. The upper atmosphere becomes part of the guidance process itself, not merely an obstacle to endure. Whether used in a specific mission profile or not, the principle reflects how carefully the entry path is matched to the capsule's design. During the most intense phase of heating, communication with Earth can be interrupted. The plasma around the capsule can interfere with radio waves, creating a temporary blackout. This happens because the ionized gas affects how electromagnetic signals travel. The blackout is expected and brief, but it means that for a short time the spacecraft continues without direct communication. The capsule remains under onboard guidance, following a predetermined entry profile while its systems record performance data for later transmission. Inside the capsule, the structure shields the crew from the extreme conditions outside. The outer surface may face temperatures of several thousand degrees Celsius in the shocked gas. Yet the inner cabin remains within habitable limits because of layered thermal protection, structural insulation, and careful design. The difference between outside and inside is one of the most striking achievements of entry engineering. A violent thermal environment exists only a short distance from a controlled human space. The upper atmosphere itself is not uniform. Density changes with altitude, solar activity, and local conditions. Heating and drag therefore depend on both the spacecraft's path and the state of the atmosphere at the time of entry. Models and measurements provide strong guidance, but slight variations are always possible. It remains uncertain in advance exactly how every small fluctuation will appear on a specific return, which is why the guidance system is built to respond within acceptable limits rather than depend on a perfectly fixed atmosphere. As Artemis II moves deeper into this region, the balance between speed, heating, and control defines every moment. The capsule continues to slow, the heat shield continues to ablate, and the plasma sheath remains wrapped around the vehicle as a consequence of compressed, superheated air. The mission's danger is concentrated in these invisible and luminous processes, where ordinary atmospheric gas becomes a force capable of destroying an unprotected vehicle in minutes. Yet the interaction remains governed by known physics. The capsule does not resist the atmosphere through strength alone. It survives by shape, material, angle, and motion, each matched to the others. In the upper atmosphere, Earth begins to reclaim the spacecraft not through gravity alone, but through air. The first molecules become a flow, the flow becomes pressure and heat, and the journey home passes through a layer of sky transformed by speed into fire. Below the highest reaches of atmospheric entry, the spacecraft descends into denser air where speed continues to fall and control shifts from thermal survival to managed deceleration. The extreme heating of the upper atmosphere begins to ease, though the vehicle is still moving quickly and remains under substantial aerodynamic load. The capsule now passes through layers of air that contain far more molecules in each volume than the tenuous heights above. These lower layers change the character of the descent. The main danger is no longer the peak thermal pulse alone, but the need to reduce speed in a controlled sequence so that the spacecraft can transition from hypersonic motion to a recoverable fall toward the ocean. The atmosphere in this region grows steadily denser with decreasing altitude. Nitrogen and oxygen remain its major components, but the important change is the increase in pressure and drag. Drag is the force that resists motion through air. As the capsule meets more air molecules each second, this force rises strongly and continues to slow the vehicle. The spacecraft's blunt shape remains central to this process. It presents a broad surface to the flow, turning motion into compressed air and aerodynamic resistance, rather than allowing the vehicle to cut sharply downward. The capsule's speed, though greatly reduced from the beginning of entry, remains high enough that aerodynamic forces still dominate its motion. Guidance continues to shape the descent by controlling orientation. The capsule can still use the small lift generated by its offset shape to manage its path through the atmosphere. But this control becomes less about stretching heating over time and more about maintaining stability, limiting loads, and arriving at the correct conditions for parachute deployment. The path must remain ordered and predictable. A capsule that tumbles or reaches the parachute phase at the wrong speed or attitude would face severe risk. As the air thickens, the plasma sheath that may have interrupted communications in the upper atmosphere begins to weaken. The ionized gas around the capsule becomes less extreme as speed decreases and heating falls. Radio contact with Earth can return, allowing mission controllers to receive updated information about the spacecraft's condition. This restored communication marks a change in the nature of the descent. The vehicle is still in a demanding environment, but it is moving out of the most isolated part of re-entry and into a phase where sequential mechanical systems must function one after another with precision. The heat shield continues to protect the capsule, though the most intense ablation has passed. Its surface has already carried away a large amount of energy through controlled erosion, and now it remains as a protective barrier while aerodynamic forces continue to slow the spacecraft. The outer structure experiences buffeting from airflow and changing pressure patterns. These forces are expected and are included in the design margins. The capsule is built not as a fragile shell, but as a pressure vessel and re-entry body able to withstand substantial mechanical stress. Within the cabin, deceleration remains noticeable. The crew continues to experience elevated loads as the atmosphere removes speed from the spacecraft. These loads generally decrease from their peak values as the descent continues, but they remain an important aspect of the return. Seats, restraints, and cabin layout are designed to support the body during this phase, distributing forces in a controlled way. Human return from lunar distance is not only an engineering problem of heat and structure, it is also a physiological problem, where the crew must endure the changing forces while remaining secure and protected. At the appropriate speed and altitude, the descent begins its transition to parachute-assisted slowing. This sequence does not begin with the main parachutes at once. A staged deployment is used because the loads are still too great for the largest parachutes to open safely at higher speed. First, small mortar-fired devices or pilot mechanisms deploy drogues. Drogue parachutes are smaller parachutes used to stabilize and slow the capsule before the main canopies appear. They help reduce the remaining speed and orient the spacecraft properly, creating the right conditions for the next phase. The deployment of drogues is a critical event. The parachutes must emerge into a fast-moving airstream, inflate in a controlled manner, and avoid tangling or asymmetric loading. The capsule's attitude at this moment matters greatly. The earlier aerodynamic descent is designed in part to ensure that the spacecraft reaches this stage in the correct orientation and within the proper speed range. Once deployed, the drogues add substantial drag and further steady the capsule's motion, transforming the descent from a mostly body-controlled aerodynamic fall into a parachute-governed sequence. After the drogues have done their work, the main parachutes are released in stages. The main parachutes are very large fabric canopies designed to produce enough drag to slow the capsule to a survivable splashdown speed. They do not open all at once into their full shape. Reefing stages are used, meaning the parachutes open partially at first and then expand more fully in steps. This controlled opening prevents sudden loads from tearing the fabric or shocking the spacecraft structure. Each stage of inflation is timed to match the falling speed and surrounding air density. With the main parachutes open, the nature of motion changes again. The capsule is no longer descending at extreme speed through dense air. It is falling much more slowly, suspended beneath the canopies, with drag now greatly exceeding the weight-adjusted fall rate that existed before. Oscillations can occur as the capsule swings beneath the parachutes, but the system is designed to limit and damp those motions. The air below is thick enough to support the parachutes effectively, and the descent becomes visibly and mechanically calmer. Weather now begins to matter more directly. Wind patterns in the lower atmosphere can influence the final drift of the capsule. Forecasting and tracking account for this, helping recovery teams anticipate the splashdown location. Rain, cloud, and sea state conditions below are important operational factors. Though they do not change the basic physics of parachute descent, the parachute system is designed to function across a defined range of atmospheric conditions expected for recovery. The lower atmosphere descent is therefore a layered process of controlled slowing. First, the atmosphere strips away the great speed of lunar return. Then the capsule stabilizes within denser air. Then drogues deploy to prepare the final transition. Then the main parachutes open in stages and carry the spacecraft toward the ocean at a much safer speed. Each step depends on the one before it. None can be improvised in the moment. The system works because shape, heat shield, guidance, structure, and parachutes all belong to one continuous design. By the end of this region, the violence of re-entry has yielded to the measured fall of parachute descent. The capsule remains enclosed by air now, no longer surrounded by plasma and shock-heated gas, but by the ordinary atmosphere of Earth. The speed has dropped from the immense values of deep space returned to a controlled rate suitable for impact with water. Above, the parachutes hold the craft in a deliberate suspension. Below, the ocean surface rises slowly into relevance as the journey through air approaches its final stage. Below the descending capsule, the recovery zone spreads across the open ocean as the final inward region of the mission. After the long path through gravitational fields, deep space, and atmosphere, the spacecraft now approaches a moving surface of water shaped by wind, current, and swell. This is not an incidental ending place chosen only for convenience. Ocean recovery forms an essential part of the design of human space return. Water provides a broad landing area, reduces the need for precise ground touchdown systems, and absorbs impact more gently than a hard surface, when descent is properly controlled by parachutes. Artemis II approaches this region as a spacecraft that has already survived the most severe thermal and aerodynamic demands of the journey. Yet the final return still depends on controlled contact with the sea and the rapid work of recovery teams. From above, the ocean appears as a textured surface of reflected light and shadow. Wave patterns extend across the water in long lines or irregular patches, depending on wind conditions and local weather. The recovery zone is selected in advance based on trajectory, safety, sea state, and the ability of ships and aircraft to reach the landing point efficiently. Forecasts of wind, cloud, and wave height help shape the final operational decision. The spacecraft does not aim at a single exact point in the way a guided aircraft might target a runway. Instead, it descends into a planned area, with the parachute system and atmospheric drift determining the final location within that region. As the capsule nears the sea, its speed has already been greatly reduced by the parachutes. The remaining descent is steady and comparatively slow, but impact with water is still a real mechanical event. Water yields, but not instantly or without force. At splashdown, the capsule transfers momentum into the surface, producing a brief deceleration that the structure and crew must withstand. Seats and restraints continue to support the crew at this moment, and the lower structure of the capsule is designed to distribute the load. The angle of contact matters. The capsule is intended to meet the water in a stable orientation, minimizing lateral impact and reducing the risk of excessive rolling. The moment of splashdown marks the end of flight but not the end of hazard. Once in the water, the capsule becomes a floating vessel with limited stability characteristics determined by its shape, internal mass distribution, and sea conditions. This spacecraft is built to float in an upright condition known as Stable 1, with the apex upward and the base down. However, under certain impact or wave conditions, it may come to rest in a less favorable orientation. Recovery systems account for this possibility. Uprighting bags, inflatable devices attached near the top of the capsule, can be deployed to roll the spacecraft into the correct position if needed. Observations from previous recovery testing indicate that this capability is essential for ensuring safe crew egress and stable towing. Salt water introduces its own practical concerns. It is conductive, corrosive, and capable of affecting exposed external components. Seals and protective coverings limit intrusion into critical areas, but the spacecraft is not intended to remain in the ocean for long periods. Recovery forces therefore move toward the capsule quickly after splashdown. These teams typically include ships, helicopters, small boats, divers, and medical personnel. Their role is not only to retrieve the spacecraft but also to assess its condition, secure it against movement, and support the crew after the stresses of return. Tracking the exact splashdown point depends on several systems. During descent, the spacecraft transmits location data, and recovery forces also track the parachutes and capsule visually and by radar. Weather and sea conditions can shift the landing point slightly relative to predictions. Recovery planning therefore includes a margin of flexibility, with teams positioned to respond across a defined area rather than a single coordinate. As small boats approach the floating capsule, the first tasks are inspection and stabilization. Specialists assess whether the vehicle is upright, whether any propellant hazards remain from the attitude control system, and whether the surrounding parachute lines present entanglement risks. The parachutes themselves may still float nearby on the surface, moved by wind and current. They must be managed carefully to avoid pulling on the capsule or interfering with recovery operations. Sea anchors or other stabilizing equipment may be attached to reduce drift and limit rotation. The crew inside the capsule experiences a significant transition during this stage. After the controlled environment of spaceflight and the intense forces of re-entry, the motion of the ocean can feel irregular and unfamiliar. Even moderate waves can produce rolling and pitching that affect balance and comfort. Medical and operational support therefore begins as soon as access is possible. The crew may remain inside for a period while the capsule is secured, conditions are confirmed, and recovery teams prepare for safe extraction. The recovery ship serves as the final platform of return. Modern recovery methods for Orion involve bringing the capsule aboard using a well deck or similar controlled system, rather than relying only on crane lifting in open water. This approach reduces motion and improves stability during retrieval. Lines are attached, the capsule is guided into position, and the ship encloses the water-filled compartment around it before dewatering and securing the vehicle. This process reflects lessons from earlier programs and extensive testing, where minimizing uncontrolled motion during retrieval proves essential. The ocean recovery zone also represents the last stage of environmental exposure for the spacecraft. The vehicle that has crossed cislunar space, endured radiation, passed behind the Moon, and entered Earth's atmosphere through plasma and fire now rests in ordinary seawater under open sky. The transformation is striking not because the laws of physics have changed, but because the scale of the environment has narrowed from the vast Earth-Moon system to the immediate movement of waves against a floating hull. Safety in this region depends on coordination between engineering and operations. The spacecraft must survive splashdown structurally and remain habitable afterward. Recovery forces must reach it quickly, stabilize it, and manage the transition from flight system to transported object. The crew must be protected not only from injury but from fatigue, disorientation, and the physical strain of return from space. Every part of this sequence is planned in detail because the mission is not complete until both spacecraft and crew are secure. Within the ocean recovery zone, the journey home becomes fully terrestrial again. Gravity is now ordinary, air is breathable, and the horizon is shaped by sea and sky, rather than by planetary curvature seen from space. The spacecraft no longer travels between worlds. It floats, waiting to be taken aboard. Human exploration, after reaching outward through the space between Earth and Moon, returns at last to water, weather, and the measured work of hands on cables, boats, and steel decks. The mission comes to rest not in triumph or spectacle, but in a quiet return to ordinary elements. The ocean moves beneath the capsule in repeating swells. Salt water touches the outer shell that only minutes earlier passes through plasma and compressed fire. Above, the sky is no longer the black of space but the layered blue of Earth, shaped by air, light, and distance in familiar ways. Recovery crews move with rehearsed care, securing the vehicle, checking its condition, and preparing to bring the crew back into the world of wind, gravity, and sea. Artemis II reveals that the journey home is not the simple reversal of departure. It is the most demanding part of the mission, because it gathers every force encountered along the way into one narrow sequence of events. Gravity first lifts the mission outward through careful motion, then draws it home with increasing speed. The Moon bends the path without touching the craft. The Earth waits with an atmosphere thin in appearance yet immense in effect, a few degrees in angle. A few moments in timing, a few small corrections made far from home, all become decisive near the end. What appears from a distance as a graceful return is, in physical terms, a controlled passage through regions that each impose their own conditions. Vacuum gives way to thin air to shock and plasma to drag to parachutes, and parachutes to water. At every stage, the spacecraft survives not by resisting nature in a simple sense, but by fitting itself to natural law with precision. Shape, material, motion, and timing remain in balance until the last movement slows. Then the capsule floats. The journey between Earth and Moon closes in the oldest setting of human travel, on open water under daylight. The mission returns with new knowledge, but also with a quiet reminder that coming home from deep space depends on understanding the ordinary things as much as the distant ones: air, heat, gravity, fabric, metal, and sea.